Welcome to another Mathologer video. Last time I showed you a simple and beautiful way to derive that wonderful and apparently circle-free pi formula over there from the area formula of the circle. One of the main stepping stones in this derivation was Fermat's incredible Christmas theorem, also known as Fermat's two-square theorem. A couple of years ago, in an incredibly scientific poll, mathematicians voted Fermat's theorem to be the 10th most beautiful theorem ever. That's the result of the beauty pageant that appeared in the Mathematical Intelligencer in 1990. As you can see, Fermat's theorem is in really good company. No surprise, e to the I pi is equal to -1 at number 1. Then there's Euler's polyhedra formula, infinitely many primes, 5 regular polyhedra, the pi squared over 6 formula, Brouwer's fixed point theorem came 6th, the irrationality of root 2, pi is transcendental, and the 4-color theorem. All great stuff. Half of these I've already covered in previous videos, and the rest are definitely on my to-do list. Anyway, today we'll tick off Fermat at number 10. The two-square theorem is a very surprising result about prime numbers that even little kids can understand. However, although the theorem is very simple to state, all of the standard proofs of the theorem, devised by some of the greatest mathematicians ever, are very tricky and pretty much out of reach of non-mathematicians. Until now. What I'd like to do today is to show you a recent super simple visual proof that you won't find in any textbook, and that even most experts don't seem to be aware of. Not that I'm an expert in number theory, but certainly I had never heard of this proof before my 2019 Christmas video just 1 month ago. But then the mysterious YouTuber the137 pointed out the proof to me in the comments of my video. And with apologies to my darling children and my darling wife, this proof was my own favorite Christmas present. Thank you again very much, the137, whoever you are. Let's quickly rediscover the two-square theorem, perhaps in the way Fermat discovered it 400 years ago. Okay, Fermat's theorem is about primes, so let's start by listing the first few primes. Fermat was interested in writing each prime as the sum of two squares of positive integers. Why on earth would anybody be interested in doing that? Yes, it's sort of Pythagoras-y, but that doesn't smell like the real reason, and indeed it isn't. It may surprise you, but the problem of writing primes in this way turns out to be at the heart of a ton of amazing and important mathematics. The amazing law of quadratic reciprocity, Gaussian integers, class field theory, and so on. Over there is a whole book dedicated to the maths that originated with Fermat's question. Alright, let's get going. Can you write 2 as the sum of two integer squares? Tough one, huh? Yes, of course, 1 squared plus 1 squared. But actually, since 2 is the only even prime, it turns out to be a bit of a distraction from the main problem. So let's kick the number 2 out of the room and forget about it for this discussion. So for the rest of this video, when I say prime, I really mean an odd prime. Back to work. What about 3? Can 3 be written as the sum of two integer squares? Going through the few candidates, it's very easy to check that this is impossible. 5, well, 1 squared plus 2 squared, of course. 7, not possible. 11, not possible. 13 is another easy one, 2 squared plus 3 squared, and so on. So certain primes can be written as sums of two integer squares and others cannot. Now, how difficult is it to decide whether a given prime can be written this way? In principle, it's easy. We just have to systematically check through the integer squares less than that prime. For example, for 31, 1 squared is not possible because 30 is not a square. 2 squared is not possible because 27 is not a square. 3 squared also impossible. Nope. Of course, we can stop with 5 squared, and in fact even earlier, because the next square is greater than 31. And at this point, we can be certain that 31 cannot be written as a sum of two integer squares. So, there's a simple and systematic check for any given prime. However, and this is Fermat's theorem, there's a much, much easier way to check. There's a super simple pattern hiding in the cans and cannots over there. Can you spot it? Too few examples? Well, have a look at this longer list. Can you see the pattern now? Maybe? Well, let's first have a look at the cans. 5, 13, 17. What do all of these successful numbers have in common? Apart from being primes, of course. Well, I've tried these numbers on quite a few people, and after a while, most will notice all of these numbers are 1 up from a multiple of 4, right? 5 is 4 plus 1, 13 is 12 plus 1, 17 is 16 plus 1, and so on. So all of these numbers appear to be of the form 4k plus 1. What about the primes that cannot be written as the sum of two integer squares? Well, as you can check, none of the primes in our list are of the form 4k plus 1. What does that leave? Yes, all the unsuccessful primes are of the form 4k plus 3. And that's Fermat's theorem. All 4k plus 1 primes can be written as the sum of two integer squares, and the remaining primes, the 4k plus 3 primes, cannot. Pretty easy to state and to understand what this theorem says, isn't it? And very beautiful. Now here's a little challenge for you. Over there is a 100-digit number. Prove that it's prime. Nope, only kidding. Of course, it's hugely difficult to prove such a huge number is prime. But take my word for it, as I took some number crunchers' word for it, that number there is prime. And now, your real challenge. Can this prime be written as the sum of two integer squares? Well, with Fermat's theorem, that's an easy one. Now, I'd like to show you that new super simple proof of Fermat's theorem that I'm so excited about. However, to make it really clear how miraculously super simple this proof is, let me first tell you a little about the super complicated proofs that came before. These are due to some of the most brilliant mathematicians, and they are what I grew up with. Fermat announced his two-square theorem in 1640. However, although Fermat claimed he'd also found a proof, as far as we know, he never published one. In fact, another mathematician, Albert Girard, already stated a theorem 15 years earlier, but he also did not provide a proof. The first proof we can be sure of was, as it happens so often, by the great Leonhard Euler. 100 years after Fermat stated it, and Euler actually struggled with finding a proof for a couple of years. Here's a summary of Euler's proof, which you can find on Wikipedia. Whoa! Not hard to see why he struggled. Definitely not for amateurs, right? Among other things, the argument includes a tricky infinite descent proof by contradiction and an ingenious application of Fermat's little theorem, a theorem which we already covered in another video. As well as Euler's proof, Wikipedia lists a number of other proofs by other top mathematicians. These are some of the proofs that you'll usually find in textbooks. All of them are at least as tricky as Euler's and are only accessible to people with some reasonable background in mathematics. Of these proofs, definitely Zagier's one-sentence proof sounds like the most inviting. That is, until you read Zagier's sentence. The involution on the complicated finite set S defined by something even more complicated has exactly one fixed point. So the number of elements of S is odd, and the involution defined by swapping Y and Z has a fixed point. All clear? Well, maybe not. So 3 years ago, Numberphile had a go at explaining this sentence in 2 videos. The videos featured the German mathematician Matthias Crack, and I don't think I could have done a better job explaining Zagier's proof to Numberphile's audience based on my understanding of this proof back in 2016. However, the videos didn't really motivate Zagier's proof and didn't explain the central and very tricky part of the proof, that strange function there. In the end, after watching the videos, you were still left with the feeling that Zagier's proof just dropped from the sky. I'm not saying this in order to criticize Crack or Numberphile. By telling you about Euler, Zagier, Crack and all those other great mathematicians, I'm just prepping you so that you will really appreciate the simplicity of the visual version of Zagier's proof that I'm about to present to you. The really easy part of the theorem is to show that none of the red 4k plus 3 primes can be written as the sum of two integer squares. In fact, this part of the theorem is not only true for primes, but for absolutely all integers of the form 4k plus 3. I already gave the short proof at the end of the last video, so you can either go back and look at that or consider it a little challenge. What I'll focus on today is the much trickier part to show that any 4k plus 1 prime can be written as the sum of two integer squares. Okay, to start, let's suppose we have a 4k plus 1 prime in hand. And let's imagine it can be written as the sum of two integer squares. What do we know about those squares? Well, since p is an odd number, one of the squares has to be odd and one has to be even. It's easy to see that two odds and two evens are both impossible. What shall we call the odd number? Well, let's go for something super original like x. Now, it's the even bit that we'll focus on, so let's write the even integer as 2y. 2y in brackets squared, that's just 4y squared. All good, though it's hard to see how it helps. It feels that we're pretty stuck, so a fairly standard approach at this stage is to consider a related but more general problem with more easily spotted solutions. Then, with luck and with fingers and toes all crossed, these general solutions may provide some insight into our original problem. In our situation, a natural way to gain more space to maneuver is to change one of the y's in our formula into a z. And now there's at least one super easy solution to our new, more general equation. Can you spot it? Not yet? Well, here's a hint. Remember that p was a 4k plus 1 prime? See it now? Well, the 4's in the two equations match, and of course 1 equals 1 squared and k equals 1 times k. So choosing x and y both equal to 1 and z equal to k will do the job. It's definitely not clear how that helps with our original problem, but let's keep going. Along with the basic 1,1k solution to our new equation, there are in general many other solutions as well. And for any particular prime, these other solutions are also easy to find. Let's have a look at an example. 37, which is a 4k plus 1 prime. So the basic solution for 37 is 119. And here are all the other solutions. In the end, the solutions we are really interested in, if they exist, are the ones for which y equals z. Why? Because any y equals z solution translates back to the solution of our original equation, into a way of writing our prime as a sum of integer squares, like this. Right? Turns back into the square. Cool! Next important observation. What if y and z are not equal? Well, then swapping y and z in a solution gives another solution for free. Like here. Swap 1 and 3 and we get this second solution. Easy, right? So solutions with different y and z are paired up by switching y and z. There's one pairing, there's another pairing, third pairing. But the solutions we are really interested in and hoping for with y and z equal sit by themselves. Okay, now the next important observation is the key to the whole business. When you take a couple of 4k plus 1 primes and actually calculate all the solutions of this new equation, it seems that there's always an odd number of solutions. For our example 37, for example, there are 1, 2, 3, 4, 5, 6, 7 solutions, and 7 is an odd number. The next 4k plus 1 prime is 41, and you can easily check that 41 has 11 solutions. Again, an odd number of solutions, and so on. Now, what if we could prove that for any 4k plus 1 prime, there's always an odd number of solutions? Well, actually, then we would have proved Fermat's theorem. Why? Well, the solutions with y and z not equal come in pairs, and so in total give us an even number of solutions. But if the total number of solutions is odd, that means there's at least one more solution around, and this solution must be of the special y equals z type. Got it? And so now we have Fermat's two-square theorem cornered. To finish the proof, all that remains to do is to convince ourselves that for any 4k plus 1 prime, our more general equation has an odd number of solutions. And the magic to come is a super nifty visual way to see that odd number of solutions. Okay, we're out to prove that for 4k plus 1 prime, our general equation has an odd number of solutions. To motivate the idea for our proof, let's focus on the highlighted solution for 37 over there. Now let's turn this equation into geometry. So 37 is equal to 3 squared plus 4 times 7 times 1. 3 squared, that's the area of a square of side length 3. And 4 times 7 times 1, that's the area of 4 rectangles with sides 7 and 1. A famous and prettily symmetric arrangement of a square and 4 rectangles is this windmill. So this windmill is a geometric counterpart of one solution to our equation. In particular, the total area of the windmill is 37. Also, if we swap 7 and 1, the corresponding windmill looks like this. Whoa, nice, huh? Okay, let's just swap back. And here are all 7 windmill solutions for 37. Pretty. Now, the straight cross down there corresponds to our basic 119 solution. And these are the pairs corresponding to swapping y and z. 1 pair, 2 pairs, and there's the third one. And that last windmill corresponds to our critical y is equal to z solution. Okay, back to the example we started with. Now here's the magic trick. Can you see another solution hiding in this windmill? No? Well, maybe step back a bit and squint your eyes. See it now? Well, ready or not, here it comes. There. A second windmill solution just appeared out of thin air. Of course, the new windmill still has a total area of 37, but now the square has side lengths 5, and so x is equal to 5, and the rectangles have side lengths 1 and 3. Looking at any of the other windmills, you'll usually also have a second windmill jump out at you. For example, if you're facing a windmill like the one over there, whose core is all green, we get a second windmill by cutting into the middle along the windmill blades like this. There, have a look. In the middle, and you see the square appearing, and there's the second solution. This new solution and the original solution are related by their windmills having congruent underlying footprint. Okay, let's have another look at all our solutions. As you can see, arranging these windmills by congruent footprints gives another pairing. There. The only exception is the footprint of the straight cross windmill, which occurs just once. In general, it's always true that the footprints of the twisted windmills come in congruent pairs. Showing this requires ticking off a handful of different cases for how the rectangle blades can wrap around the square core. Not hard, however, also not boringly trivial and without its own charm. Maybe give it a go yourself, and if you get stuck, follow the link in the description to this summary. As well, it's definitely clear that footprints of straight cross windmills occur just once. And there's always at least one such straight cross windmill corresponding to the basic solution. However, conceivably, in general, there could be a few such straight crosses, right? There, apart from this basic straight cross, maybe there's also a straight cross like this, or one like that. However, it turns out that only the basic straight cross ever occurs. And here's how you can see this. For a straight cross, the side length x of the square is the same as the side y of one of the rectangles. That means in the equation we can replace y by x. Pull out the x. So in the case of a straight cross, the number p is a product of two integers. But since p is prime, it only has two factors, 1 and p itself. And so it's clear that the smaller factor, which is x, must be equal to 1. However, x is equal to y for a straight cross, and so y is also equal to 1. And so we conclude that for absolutely every 4k plus 1 prime, there's only the one straight cross corresponding to the basic 1,1k solution. But remember, all the other twisted crosses come in pairs, giving an even number of twisted crosses. And an even number plus 1 is odd. Ta-da! The number of solutions is always odd. What a bloody amazing proof. There was quite a bit there. So just a quick recap before we continue. We used the windmill pairing to show that there is an odd number of solutions. This implies, via the yz swap pairing, that there is one critical solution in which y is equal to z. And so 4yz is a square, and therefore pi is a sum of two squares. Nice, 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 nice. And what I've gone through for you is really just a visual version of Zagier's proof. In particular, the very clever windmill pairing corresponds to the tricky central part of the proof that was skipped in the number file videos. For those of you who fought with understanding Zagier's proof, let me just point out that the three cases here correspond to three different ways the windmill blades can wrap around the inner square. Now, I've not been able to find out who we have to thank for discovering the beautiful windmill interpretation of the tricky part of Zagier's proof. Maybe one of you knows, in which case definitely make it known in the comments. Anyway, I've linked to what I do know in the description of this video, and I'll update this information if I find out more. We've proved that any 4k plus 1 prime can be written as the sum of two integer squares. But there's an extra neat and very important aspect that I haven't mentioned yet. It turns out that a 4k plus 1 prime can be written as a sum of two squares of positive integers in exactly one way. For example, over there, 2 squared plus 5 squared, that's the only way for 29. Okay, yes, there's also 5 squared plus 2 squared, but unlike in the last video, we won't distinguish between these two trivial variations of writing the same sum. I'll show you a proof for uniqueness in the next chapter, but first a fun windmill interlude as a bit of light relief. Are you familiar with the 2007 Spanish movie Fermat's Room? No? Then forget all the Marvel stuff and go watch it. In this movie, a group of mathematicians are trapped in a shrinking room, an absolute must-see. Fun fact, to enable the four walls of Fermat's room to contract, they are arranged in the shape of a windmill. There, if those are the walls of the room, they contract like this. That windmill configuration is really very versatile, isn't it? Now, apart from proving Fermat and murdering mathematicians, here's another very pretty application. A windmill consisting of a square surrounded by four copies of another square, that's what the windmills of the critical solutions of our Fermat equation look like, right? Well, this diagram happens to also be very interesting mathematically outside our proof of Fermat's theorem. First, the windmill can be extended to this non-obvious tiling. Nice, huh? Even more interesting and related to the Pythagorean aspect of Fermat's theorem, you can use the tiling to prove Pythagoras' theorem. Want to see how that works? You do? Well, of course you do. So what we want to prove is that in this right-angled triangle, the area of the two smaller squares is equal to the area of the larger square. A squared plus b squared equals c squared, right? Okay, so tile as before with copies of the two smaller squares. Now you can check that a square tiling consisting of copies of the large square aligns neatly like this. Focus on one each of the different tiles. So the large square is cut into a few little puzzle pieces. And it's easy to see that these puzzle pieces reassemble into the pieces for the two smaller squares. And this shows that the area of the two smaller squares is equal to the area of the larger square. So, there you have it. A very pretty windmill-based proof of Pythagoras' theorem. Finally, for you really serious methodologists who can handle a little more, let me round things off with one more proof. Let me prove for you that a 4k plus 1 prime can be written as a sum of two squares of positive integers in exactly one way. Now, this is a typically crazy number theory proof with letters flying around all over the place. It's also another opportunity for you to appreciate how incredibly nice the Zagier windmill proof really is. To begin, there are definitely numbers that can be written as a sum of two squares of positive integers in more than one way. For example, 50 over there or 325. Now, in terms of our 4k plus 1 primes, we've already proved that any such prime can be written as a sum of two squares in at least one way. What remains to prove is that there can never be more than one way. Okay? Well, let's begin. Suppose you're given two numbers that are both sums of two integer squares. Then the product of these numbers is also a sum of two integer squares. This follows from a famous identity that was already known to the ancient Greeks. Here it is. We obtain a second version of the identity by swapping the plus and minus in the brackets at the bottom. And now to the primes. Suppose we have a 4k plus 1 prime, and let's assume that a squared plus b squared and c squared plus d squared are two different ways of writing p. Then using our Greek identity, we can see that p squared is also the sum of two integer squares. And the second version of our identity gives a second way of doing this. We'll need these two identities later, so let's just store them away for the moment. Next, solve for b squared and d squared. To make the right sides of these equations equal, we multiply the first equation by d squared and the second equation by b squared. Okay, now since the right sides are equal, the left sides are also equal. And we get this new equation. Now collect all the p's on the left-hand side and factorize. This is just autopilot here. Okay. Right? On the right, we have a difference of two squares. Let's also pull it apart as usual. Getting there. Remember, p is a prime, and so p must either divide the red term or the blue term. Also, what's promising is that the red and blue numbers appear in the identities that we tucked away. So let's untuck them. Okay, so p definitely divides either the red or the blue. Let's first assume that p divides the red. Now, p dividing red means that p is equal to 0, or p, or 2p, or 3p, or any other multiple of p, right? But if red is not 0, if it's a non-zero multiple of p, then red squared would be equal to p squared or larger. But that would make the right side of the equation greater than the left side, which is impossible. Therefore, we conclude that red is equal to 0. But now return to the top equation. If red equals 0, that means that the right side of the top equation is 0. And so d squared has to be equal to b squared. Skipping back to the very beginning, this implies that a squared is also equal to b squared. There, like this. Again, autopilot. Cool. But that means that the two ways of writing our prime as the sum of two integer squares that we started with have to be the same. Okay. Summarizing that argument, we've seen that the first possibility, that p divides red, implies that any two ways of writing p as a sum of two integer squares must be the same. And so, on to the second case, where p divides blue. If this case gives the same conclusion, then our proof is finished. We'll have shown that there is no more than one way to write our prime as the sum of two squares. Okay, take a deep breath. Now, suppose p divides blue. Then because blue cannot be 0, it has to be equal to p. Why? Because otherwise the left side of the equation would definitely be smaller than the right side. Okay, so the blue is equal to P. Then AC is equal to BD, right? There. AC is equal to BD. Again, let's skip back to the beginning to see what this extra information gives us. Now notice that A and B cannot have a common factor, other than 1, of course. Why? Because if they did, then P would have that same factor, and that's impossible since P is prime. Let that sink in for a bit. All good? Great. But then, because AC is equal to BD, the number A has to divide D, and B has to divide C. That, right? Now, P is also C squared plus D squared. Huh? With C and D at least as large as B and A, how's that going to work? Well, clearly, the only way is if B equals C and A equals D. And so, as before, we conclude that the two ways of writing P as a sum of integer squares are the same. And this finishes the proof that there is exactly one way of writing a 4k plus 1 prime as a sum of two integer squares. Like this? Well, I really like this too. Phew, anyway, lots of A's and B's and so on zinging around there. So definitely don't stress if you didn't catch every detail of this proof in the first go. Also, if there are any parts of this video that you struggled with, just ask in the comments. As always, there will be lots of very cluey people watching this video who will be happy to help. The uniqueness argument that I just showed you may seem much more involved than the Zagier windmill proof, but really it's much easier. For the most part, we just had to follow our nose using well-known ingredients such as that Greek identity. True, we had to follow our nose a pretty long way, but coming up with an argument like this is really a trivial task compared to the ingeniousness of Zagier's proof and its windmill incarnation. Finally, a very easy challenge for you. We've been working hard on sums of integer squares, but what about differences? Your challenge is to show that a non-zero integer can be written as the difference of two integer squares exactly if the integer is odd. And the second part of the challenge, show that this way of writing an odd integer is essentially unique if the integer is prime. And that's it for today. Except I'd like to thank all of you who've taken out a Mathologer membership via my new Patreon page or supported Mathologer directly via PayPal donations. I really appreciate it. From this video on, the names of all supporters of Mathologer video will appear in the credits. I guess that means you'll be remembered forever, or at least as long as YouTube exists. And thank you all very much again for supporting Mathologer simply by watching and engaging. Until next time.